All right, it's 11. We will get started. Some announcements for you all. Just a reminder that the Chapter 3 Part 2 Achieve is due Monday at 9 a.m. The Chapter 3 learning curve is posted, so that's that extra credit adaptive quiz. There will be one per chapter available. That's due October 20th, which is just after the midterm exam, so you have a while to do it, but feel free to do it now since we'll be finishing Chapter 3 today. Another reminder that the McLean lecture is tonight at 6:30 in this room, and to arrive a few minutes early if you plan to attend, so that you are not kicked out, but so that you are not let in. Professor Cunningham teaches one of the 3 sections of 1070, and she is hosting just general chemistry office hours. So I mentioned this on Wednesday. They are 2 to 4 p.m. Wednesday and Friday in C117, which is right across the hall here next to the main office. Therefore, I think 4 different general chemistry classes, and so it's just a time for anyone in those gen chem classes to go and ask her questions. So feel free to use those office hours to your advantage. You might have noticed I didn't post Chapter 4 notes for today. I changed my mind and I figured we'd just finish Chapter 3, and I do have your exam. So I'll pass them out after we're done going through the lecture notes, and then we'll talk about that. So we ended last class with this iClicker question where we are given an empirical formula and we are trying to determine the molecular formula. So you all already answered this, but I think it will be helpful to just go through this question. We didn't all get the same answer. So remember that when we're given an empirical formula, to determine if that is the molecular formula, we need to compare formula masses, or the molar masses of the entire formula. So we find the ratio N, which is the molecular formula mass, divided by the empirical formula mass, and that will give us some integer. That integer is what we multiply the subscripts by. So in this example, the empirical formula is CH2O, so we need to find the molar mass of CH2O. So that's 2 times the molar mass of carbon we'll put in units, grams per mole, plus, 1 time the molar mass of carbon, 2 times the molar mass of hydrogen, and 1 times the molar mass of oxygen. Now, I had a question in office hours that I wanted to bring up here. I have used different values for atomic masses for different elements. You may have noticed that. Sometimes for oxygen, I have 16.00, sometimes 15.00, 99999. Whenever you're going through homework, doing homework questions, use the periodic table. I'm going off memory, so that's why sometimes I'll use 16.0, sometimes it's 15.999. I will try to be consistent from now on. I'm glad that I forgot who asked me that question, but I'm glad they asked me. But just keep in mind, when you're doing your homework, just use your periodic table. Some have 2 decimal places, some have 3. It doesn't matter. Whatever periodic table you have, you should get to the right answer. You should use what's on the periodic table that you have for the test. So maybe just plan on using that when you're doing homework. Oh, it did? Okay. The 3 decimal places? Okay. That's good to know. So on the Achieve homework, they want the more precise atomic masses. Thank you. Okay, so if we add all of these together, I actually don't have what this is. So I have to add it together. I have, does 19.025, does that align with what you all have? No? Okay. Punch something in wrong. 39? Okay. Yeah, okay, I have 30.025. That feels better. Okay. So that's our molar mass of the empirical formula, which is not the same as the molar mass of the molecular formula. So now we find the ratio between the two, which we use the letter N to represent. So we use molecular formula molar mass 180.16 grams per mole divided by the empirical molar mass 30.025 grams per mole. And this is approximately 6. That ratio is 6. So that means however many atoms we have in the empirical formula, we have 6 times as many atoms in the molecular formula. So the molecular formula is the empirical, where we multiply each subscript by that integer of 6. So C 1 times 6, H 2 times 6, O 1 times 6. We get C6, H12, O6. Yes. What do you say? No, so we're actually not going to do iClicker today. One day off. This was an iClicker from last session. Yeah. Go ahead. N is, do we use that letter to represent this ratio? So N is the ratio between molecular and empirical. So here N equals 6. The bottom, what we calculated up here. That's the molar mass of the empirical formula. So it's the grams per mole value of the empirical formula, which is CH2O. Yes. 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 And then we know by comparing molar masses that this is the molecular formula of this molecule. Okay. Other questions? Okay, we're going to move on to the last section here, combustion analysis. So combustion analysis is a lab technique to help determine the empirical formula of a sample that has carbon, hydrogen, and possibly oxygen that is burned through combustion. So we can use the amounts of products produced to determine the empirical formula of the sample that was burned. So when something containing carbon and hydrogen, or carbon, hydrogen, and oxygen is burned in oxygen gas in O2, that produces carbon dioxide and water. Those are the only two products. And there can be some excess oxygen as well, but those are the only two new products. So here's an example where we have C4H10 reacting in the presence of oxygen gas that produces carbon dioxide and water. So if you don't, well, let's just look at this combustion analysis apparatus. So if you have a sample in the combustion chamber, this is the carbon, hydrogen, and sometimes oxygen molecule. We have a stream of oxygen gas going through this combustion chamber. These sample is burned and reacted with the oxygen gas. It produces water, CO2, and if there's excess oxygen gas, then that is released as well. So then the products go through the series of chambers. This first chamber is absorbent for H2O, for water. So any water that's produced will remain in this chamber. And then the second one is absorbent for CO2, carbon dioxide. So any CO2 that's produced will remain in this chamber. And then excess O2 can then be released. So once a sample is burned through this apparatus, you can then determine the mass of water that's produced by measuring the mass of water that is contained within this chamber, and the mass of carbon dioxide that's produced by measuring the mass of carbon dioxide that's contained within this chamber. So if you know the mass of H2O and you know the mass of CO2, then we can calculate the empirical formula based on masses of these atoms of the sample that is reacted. We go to this next slide here. Every carbon atom that is reacted in combustion is then produced in a carbon dioxide molecule. So CO2 product contains every carbon atom that was reacted in the original sample. So if we know the mass of CO2 produced, then we know the mass of carbon produced, and that's the same as the mass of carbon reacted. So this follows the law of conservation of mass, which we covered in a previous chapter, where however much mass you start with in a reaction, you're going to end with the same amount of each atom. So if we know the mass of carbon dioxide, we can then determine the mass of carbon produced, which is equal to the mass of carbon reacted, by converting mass of CO2 to moles of CO2 and for every 1 mole of CO2, we have 1 mole of carbon. Because its formula is CO2, there's 1 carbon in every CO2 molecule. Every 1 mole of CO2 has 1 mole of carbon. So now we can convert to moles of carbon. 1 mole of carbon for every 1 mole of CO2. And then we convert moles of carbon to mass of carbon using its atomic mass. And this would give us the mass of carbon produced, which is the same as the mass of carbon reacted. So we don't have actual values for this equation here as far as the mass of CO2 produced, so we're not actually calculating the mass of carbon here. But if you were completing a problem where you do know the mass of carbon dioxide produced, then you can find the mass of carbon that is reacted. And then we can do the same thing for hydrogen. So all of the hydrogen atoms that are reacted in a combustion reaction are produced in water. So the H2O product contains every hydrogen atom that was reacted in the original sample. So we can do the same thing using the mass of H2O produced to determine the mass of hydrogen that is reacted. We have a similar equation, mass of H2O. If we're looking for mass of hydrogen, we need to convert to moles of hydrogen. We can convert to moles of hydrogen by first converting to moles of H2O. So 1 mole of hydrogen of H2O, 18.02 grams. And then for every 1 mole of water, we have 2 moles of hydrogen. That's because of its formula, H2O. So 2 moles of hydrogen for every 1 mole of water. And then we use a molar mass of hydrogen to convert to mass of hydrogen. So once we know the mass of carbon reacted and the mass of hydrogen reacted, all we have is carbon and hydrogen in the reactant. I'm going to go back a couple of slides. I'll come back to the one that we're working on. But if you remember this table where we were determining an empirical formula, we start with the masses of each element in the formula. We convert to moles in that first step, and that gives us the molar ratio. And then we simplify by dividing by lowest number, multiplying by an integer if we need to. So if we know the masses of carbon reacted, the mass of hydrogen reacted, then we convert to moles of each. Then we have our molar ratio, and we can find the formula. So this slide shows how we get mass of hydrogen. The previous slide shows how we get mass of carbon. We're going to do an example on this next slide together. So naphthalene is a white solid, consists of only carbon and hydrogen. So we're only looking for mass of carbon, mass of hydrogen. It's once used as the active ingredient in mothballs. When a combustion analysis was carried out on 5-gram sample of naphthalene, it produced 17.17 grams of carbon dioxide and 2.81 grams of water. So this question gives us the molar mass of naphthalene and is asking for the molecular formula. So we will first determine the empirical formula and then follow the steps that we did for that iClicker question at the very beginning of class to then determine the molecular formula using the molar mass information. But let's start with combustion analysis. Luckily the screen is pretty big. In my earlier class we have a small screen and I have to write pretty small for this question because there's a lot involved here. But our first step is determining how much carbon was produced, which is equal to how much carbon was reacted, and then same thing for hydrogen. So we'll follow those steps that we did on the previous 2 slides. We have 17.17 grams of CO2. This is the information we start with to find the mass of carbon reacted. So we convert to moles of CO2. Using the molar mass of carbon dioxide, we find that by adding molar mass of carbon and the molar mass of oxygen times 2. And then for every 1 mole of carbon dioxide, we have 1 mole of carbon, so we can now convert to moles of carbon. And then once we're in moles of carbon, we can convert to mass of carbon using the atomic mass of carbon from the periodic table. So this equation, canceling everything out, so oops. Cancel out grams of CO2, moles of CO2, moles of carbon, and we're left with grams of carbon. So we have 4.69 grams of carbon. That is the amount of carbon in the original sample. Let's see, mass of carbon. Now we need to do the same thing for hydrogen. Our naphthalene contains carbon and hydrogen. So we have 2.81 grams of water produced. Converting to moles of water. And then for every 1 mole of water, we have 2 moles of hydrogen. So 2 mole hydrogen over 1 mole of water. And then converting to mass of hydrogen using its atomic mass. Yes.
For the first one, like for the CO2, why didn't you go 4 6 things instead of 3? Or does it not matter?
Yeah, it doesn't matter for this one. Good catch though. If you were asked for sig figs, then it would matter. But here, this is sufficient. Okay, so we have the masses of the 2 elements that are present in the original sample. To find the molar ratio to get to the empirical formula, we need to convert to moles. So 4.69 grams of carbon, use a molar mass. And I'm just continuing from that calculation there. We have moles of carbon in the original sample, and then we do the same steps using the molar mass of hydrogen to find moles of hydrogen in the original sample. Yes. To get the moles. In this, yeah, so we would multiply, I mean, technically we're dividing by the molar mass because we have the grams at the bottom. But we multiply by this fraction, we put grams at the bottom to cancel out grams, and then we end with moles of each atom using its molar mass. So now that we have the moles of carbon and hydrogen, we can put together the empirical formula. C 0.391 and H 0.312. We have 2 decimals. We need to divide by the lowest number. So divide by 0.312. And this provides C1.25H1. So after dividing by the lowest number, we still have a decimal. So now we're in that last row of that table of determining an empirical formula where we need to multiply by a small integer. Usually it's 2, 3, or 4. In this case, if we multiply by, yeah, you can answer your question. Go ahead. Yeah. So if we multiply by 2, if you try that out, you'd still get a decimal for carbon. If you multiply by 3, you still get a decimal. If you multiply by 4, then you get a whole number. So we multiply each subscript by 4, and we get C5H4 as the empirical formula. But we're not done yet, because they asked for the molecular formula. So we've reached the empirical formula. We are given the molar mass of the molecular formula. We need to find the molar mass of the empirical formula, compare it to the molar mass that's provided. I'll do this down here. So molar mass of C5H4. I'm not going to write out the equation just to save space, but you do 5 times the atomic mass of carbon plus 4 times the atomic mass of hydrogen. And that I have 64.082 grams per mole. Okay. So we have the empirical formula molar mass. We have the molecular formula molar mass provided. Now we need to find the ratio between the two. I'm working here now. So we use N. We do molecular formula molar mass divided by empirical formula molar mass. So molecular formula molar mass is 128.17 grams per mole. Empirical formula molar mass is 64.082 grams per mole. So if you simplify this fraction, we have an N of approximately 2. So the molecular formula is the empirical formula where we multiply each subscript by 2. So C10H8. So this question essentially combined everything that we've learned in the last few sections into one question. So that's why it's a pretty long question. But just to recap, we use the masses of carbon dioxide and water produced to find the masses of carbon and hydrogen reacted. We convert the masses of each element to moles of each element, and that gives us our molar ratio. Right here. We simplify this by dividing by the lowest number, multiplying by an integer to get whole numbers, and then we can determine if the empirical formula is the molecular formula by comparing molar masses. It's not, because the molar mass of the molecule is 2 times the molar mass of the empirical formula. So we have 2 times the amount of carbon, 2 times the amount of hydrogen in the actual molecule. So C10H8. Questions here? Okay. So this slide summarizes the steps that we did to find the empirical formula. So combustion analysis can be used to determine empirical formula. Of carbon-containing compounds. This particle picture shows we start with this molecule, C4H8O2. We have 4 carbon atoms. All 4 carbon atoms are part of the CO2 molecules that are produced. We have 8 hydrogen atoms. Those are the white circles here. All hydrogen atoms are part of the water molecules that are produced. So we can go directly from mass of H2O to mass of hydrogen, mass of CO2 to mass of carbon. But we have oxygen sometimes in the reagent and in the oxygen gas that's required for combustion to occur. So we can't go directly from oxygen in water and oxygen that's in CO2 produced to find the amount of oxygen in this molecule, because some of the oxygens over here are from the oxygen gas. So instead, if you do have oxygen in your sample, you'll be given the mass of the sample that was burned. You can calculate grams of carbon and grams of hydrogen from the analysis that we did in the last slide. And then if you take the total mass of the sample minus the mass of carbon and hydrogen, then you can find the grams of the oxygen that was part of the original sample. And the remaining oxygens were from oxygen gas. Okay, let's work on, or I'll have you all work on this question before we do it together. So we have a hydrocarbon compound. Hydrocarbon means we only have hydrogen and carbon. So you will be told either you have a hydrocarbon or you have a compound containing only carbon and hydrogen, or you'll be told you have a compound with carbon, hydrogen, and oxygen. And that's how you'll know if you need to calculate oxygen that's part of the original sample. But in this case, again, we only have carbon and hydrogen. So we have amount of CO2 produced, amount of water produced. We need to just determine the empirical formula. So you don't have to do that step where we find the ratio of molecular formula to empirical formula molar mass and multiply the subscripts. Just find the empirical formula of this compound. So I'll give you all some time to work on this. Wait.
Oh, it's 2.7. And I think it's like basically like 2/3. So it's multiplied by. That's like close to like near. I just took these yeah, I just you got the same. I don't know.
I can write reading. That's discussion. Make it into text.
Oh, yeah.
Let's say one more minute and I'll start going over it. Okay, let's start going through this together. I know some of you are still working, but I looked at a lot of your work and it looks like you all are on the right track. So we start with converting or calculating the mass of carbon reacted. So if we have 13.84 grams of CO2, we convert to moles of CO2 using the molar mass of carbon dioxide, 0.009, I think. And then because the formula for CO2 is CO2, there's only one carbon in every CO2 molecule. We have 1 mole of carbon for every 1 mole of CO2. And then we can convert to mass of carbon using the molar mass on the periodic table. And then this is 3.77. Ooh, what's happening? 3.770 grams of carbon. And then we can do the same thing for water to find grams of hydrogen. So 7.556 grams of water times 1 mole of H2O over the molar mass of H2O. And then because the formula for water is H2O, there are 2 moles of hydrogen for every 1 mole of water. Multiply my molar mass of hydrogen. And we get 0.845 grams of hydrogen. So that's the amount of carbon, amount of hydrogen reacted in the original sample. But when we put together an empirical formula, our subscripts are molar ratios. So we need to convert mass of carbon to moles of carbon, mass of hydrogen to moles of hydrogen. So we use the molar mass, 1 mole of carbon for every 12.01 grams of carbon. And this is 0.314 mole carbon. For yes, go ahead. Great question. Yes, okay. So in this original equation, when we find the mass of carbon, we convert grams of CO2, moles of CO2 to moles of carbon to grams of carbon. And then we take grams of carbon and convert back to moles of carbon. So we convert to grams and then convert to moles using the same ratio. You could just end that first equation by calculating moles of carbon and not going all the way to grams of carbon. That will give you the same answer and you skip a step. The reason we've been converting to grams is because when we were determining empirical formulas, we were starting with the masses of each element. So to follow these steps, we start with the masses of each element, convert to moles. You can do it that way, stay consistent across all of these calculations. If it makes sense in your head to skip the calculation to grams and go straight to moles, you'll get the same answer, and that's okay too. So we have grams of hydrogen, convert to moles of hydrogen. And we have 0.839 moles hydrogen. So we have the molar ratio of carbon and hydrogen. We use that to write the empirical formula. C 0.314, H 0.839. Divide by the lower number, 0.314. C1, H 2.6, 2.67, depending on how you round. So we still have a decimal at the end of this calculation, so we need to multiply by an integer. If you multiply by 2, you will still have a decimal. If you multiply by 3, that gets you really close to a whole number. So we multiply each by 3, and we get C3H8. Questions here? Yes. I would at least do 2 after. Yeah. So when you're here, don't round to 1 decimal. At least have 2. You could keep more, but yeah, I think 2 is important. Because if you have like 0.25, then you know you multiply by 4. But if you rounded that to 0.3, that's too much rounding. Yeah. Okay. Let me. Couple of things. So I'll pass back your unit exam ones. The scores are not. We all quiet down. I just have a few things to say. Okay. So the scores are not yet on Blackboard. I'll post them later today or this weekend. The way that they're graded. So each multiple choice question was 3 points, except for one. Well, no, they're all 3 points, but hold on. Give me a second here. This question here, where you are adding microliters to liters in units of microliters, with sig figs, the correct answer is 950. I'll post the key so you can look at this. You calculate 951, and with sig figs, it's 950. So each question is 3 points, but I gave you all 1 point if you pick B, because that's really close. Just not quite there. So if you have +1 there, that's because you picked B. So you'll see for each multiple choice question, either +3 next to it if you got it right, or +1 for this one if you pick B, or an X if you got it wrong. For the short answer questions, they're each out of 6 points, so you have a grade out of 6. If you did not get 6 out of 6, there is a comment there to indicate what was wrong. I will also be posting this key, and I have everything worked out on here, so you can compare your answers to the key, including the short answer questions and how I graded them. And then your total is on the back of the packet. When you get yours back, try to refrain from reacting whether it's really positive or negative, because everyone in here has a different grade. So let's be respectful to everyone in the class. Just keep it to yourself. Once you leave the classroom and you're by yourself, then I don't care. Gianna? Michael? Christina? And Laura? Grace? Michaela? Okay, who didn't get one? Okay, what are your names?
This is already.
Oh, that's
Am I though?
Yeah, I think it's like it's significant until the 1-3, but because like you move one more over because of the margin, right?
Is this what?
Is this for the learning?
No, so I haven't added that. Yeah, I think I'll do that at the end of the
Does that
semester.
go straight on this, like on the computer, or is it separate?
So I think what I'll do is at the end